All right, well, welcome to yet another lecture of 2DM3, Discrete Math with CalcCheck and Friends. As by popular demand, we will do some live CalcCheck just as before, and we have some a lo-fi mad chilled cal as was suggested, and somebody has volunteered to let me know that I'm not talking to the void, so much appreciated. So I hope everyone had a good reading week, and if not, don't worry, there will be other reading weeks, and you know, there's more to life. Please stop trying to take control. Yeah, please don't do that. Let your friends know, don't take control. Last time someone accidentally took control, and I had to split the video into 2 parts, and that's why I had some trouble uploading it. But it should be on YouTube now. So let's start off with today's lecture plan, and then we can talk about the upcoming midterm for next week. No worries, Mohammed. All right, so let's do that. Before we get there, are there any questions, concerns, or queries? Does somebody want to say no? And I'll move on.
I don't think there is, but I think someone asked if we could go through 8.6. If there's time.
Yeah, we can definitely do that. No problem. So we'll talk about the midterm at the very end, and maybe we'll talk about 8.6 as well. There's no problem. All right. So since Isra seems to be a person who has a mic and is willing to talk, if I ask a question and no one says anything, maybe Isra will just be like, algebraic, mathematical, no thank you, and I'll move on. All right. And I have the chat open on the side as always, so I'll keep an eye out there as well. Okay, that's. As somebody asked a moment ago on the chat regarding loops, so the whole point of quantifiers is to give us a mathematical formalization for loops. So here's just from last time. If you want to add up a bunch of stuff, all right, you can add up a bunch of stuff by using ... notation, right? This is like a for loop, but instead you can also write it in this quantification notation. Alrighty. And in the book, they use a general arbitrary operation like O plus or star. And so when you're starring or O plusing a number of terms, that's essentially what a quantification is. Okay. So in a sense, quantification and loops are the same thing. Okay. So if you're comfortable with quantifiers, hopefully you'll be comfortable with loops, and your knowledge about loops will come in to the knowledge about quantifiers. So today, an alternate title for today would be the theory of loops. So that would be an alternate title for today. Deny. Okay. So even if you don't know what loops are, just by talking about theorems and properties about quantifiers, we'll actually understand the nature of loops a bit better. So some properties of quantifiers can be seen as optimization rules for loops. Other axioms can be seen as definitions of loops. Okay, so just as a reminder, all right, the idea is if you say I have a running total becomes the identity of O plus, then I'm going to say I have a counter, for example, I becomes 0. Then I say while I is less than n, we're going to say the total and I are both updated such that the total becomes T O plus f at I, and I gets incremented, right? This essentially means that at the very end, box. This means at the very end, we essentially have t is equal to O plus over I with 0 less than or equal to I less than n spot f at I. Okay, so a for loop can be thought of as implementing a quantification, right? So whenever you see a quantification, you can think of it as an specification of a for loop. Okay, so a for loop is one way to implement it, right? So instead of starting at I equals 0, we might have wanted to start at I equals n minus 1 and then sum that way, or we might have started at different places. So a loop is a particular implementation of a quantification. Okay, so there's that relationship between implementations and specifications. So from the last assignment, we were talking about orders, and we mentioned, you know what, implication is an order on the booleans. Less than or equal to is an order on numbers. Divisibility is an order on the naturals, right? So a general order versus a particular implementation. Okay. Another example you might have seen is from calculus. The exponential function can be implemented as an infinite sum of factorials, but the exponential function can also be characterized very elegantly as the unique function that is its own derivative, and at 0 it's equal to 1. Right? So specification and implementation are very dual to each other in some sense. Okay, ducks. Oh, somebody can't see my text. Is that it? Control Shift A. There. Is this better? Apologies. Okay, ducks. All right. I'm just making sure I can see your words here. Okay. I tried doing a post condition backwards. Okay, I was just looking at the thing to make sure there was no questions here. Alrighty. So that's the idea of why we're interested in quantifiers. They let us reason about loops. Okay, and loops can be thought of as particular implementations of quantifiers. So let's begin there. We'll begin with loops that involve sums and products, but the book covers arbitrary loops, and eventually we'll get to universals and existentials, which are again a form of loops. So it's up to you if you want to follow a generic one or a particular one. Either's fine, and we'll cover the particular ones just so that it's easier to grasp. But the book uses a generic operation star, I think, or O plus. So either's fine. It's not a big deal. We'll use the same names though, so no worries. So this first problem says, how do you formalize the sum of the first n odd numbers is equal to n squared? So let's try doing that. Okay. So we can say the sum of the first n odd numbers is equal to n. So we can say theorem / sum I is a natural number with I is less than n. Right, so we can do that, and we can say and odd I spot I. So we can try to do that, right? And of course we have to then have a declaration for odd of type natural numbers to booleans, okay? And then we can have an axiom that says odd, that specifies what it means for a number to be odd. So that's one way to do it. Okay, so I'm just looking at that. So that's one way to do it. Unfortunately, then you have to work with this property of odd. It might not be clear. So another way to do it would be to say, all right, I know what the odd numbers are, right? And for I to be odd, it has to be of the form 2 times I plus 1, right? That's what it means for I to be odd. It has to be of that shape. So I can just change all instances of I to be 2 times I plus 1, okay? Or in the notation we have in this class, I can say, for example, the successor of I plus I, 2 times I plus 1, okay? Either would be fine. And the rule that will let us odd in the range to getting We'll get to those later on. So for now, you'll have to take it on a bit of faith, but we'll get to these later on. There are rules that will let us take a complicated range and simplify it and make the body a bit more complex. So these are very helpful rules, and we'll get to them later on. All right. So here's one formalization of the sum of the first numbers is n times n. Okay. So we'll go through the slides, and occasionally we'll pause to do some calc checks, just as we've been doing before. So we'll I've left this example on from last lecture, just to, as a reminder for some people who may have forgotten, that we can always expand these quantifications into smaller parts. And the extra space is just to show you the grouping for multiple variables. So I wanted to show you all these slides at once. Not because I'm trying to scare you at once, but just because they're familiar and there isn't that much difference. So if you want me to zoom in or to stop at a particular place, please just let me know. If things aren't big enough, let me know. Okay. So for example, this quantification expansion, here's a bigger example. We did this last time. You'll notice we have to use substitution as a keyword. So only for the first little while, quantification expansion is a key phrase you'll use. Most often, we'll use we'll use the rules about quantifiers. Okay, so this is just stuff from last time. Just wanted to remind you about it. Again, the variables go first, then the constraints, then the body. All right, as expressed right here. Okay. Again, this is all in the book, so nothing new yet. Just a review of last time. You may have seen from your calculus classes and virtually everywhere else, they use this two-dimensional notation. So you have an index, then the mix symbol, then the constraint. So you have a bunch of stuff in a line, then to the side you have a body. Okay, so it's two-dimensional. Because two-dimensional is not practical in programming, we're just going to have a linear notation. And the linear notation also forces us to give greater attention to the range, whereas where all the action happens, or most of the action happens in the range as well as in the body. Whereas the two-dimensional notation, it squeezes the range all the way down here and it makes it hard to manipulate, as we talked about last time. Okay, next. All right. So the book uses colon. We're going to use spot. All right. And the book uses just right here, like O plus everywhere, or small plus or small c dot. We're always going to use these big operators. This is just for parsing. Okay, so CalcCheck has to be able to read these. And if it sees a plus right here and more pluses, it knows it's the binary operation plus. But if it sees a plus right here, it might think, oh, it's a plus, and you gave me one thing. Where's the other thing over here? So we're going to use these big operators for parsing. Okay, ducks. All right. So just as I showed a moment ago right here about how we had even and then we got rid of it, you can have arbitrary, we had odd. You can have arbitrary constraints on your variables in the range, as it were. All right. And we'll talk about rules on how to simplify that and how to massage it to get simpler quantifiers that you can immediately solve. Alrighty. Yeah. So here is the problem we started off. So let's just do it together. All right. I'll hide some of it, I guess, so that maybe we can try to do some of it together. I can ask and see how far that gets me. So this is a problem about natural numbers. When you don't know what to do, you say, oh, the only thing I really know is that natural numbers are defined by induction. In particular, we don't have any laws about sums yet. So the best thing we can do is look at it by induction. So we'll start there. By induction on n, like that. Okay. Then we have a base case. And of course, we have an induction step. Okay. All right. So let's, time to earn some knowledge. Who wants? I do have the chat open right here on the side. If you don't want to talk, if you do want to talk, feel free to do so. But what are we doing in the base case? Does anybody want to tell me? Let I become 0. Really close, but no, we're doing induction on n. Okay, so since we're doing induction on n, n is the one that becomes 0. Good try. All right. Yeah, no, that's why you're learning. No, that's why you're learning. This is the moment to learn. Don't worry about it. Okay. So we're right here, and we replace n with 0. Okay, so that's what we want to prove. We want to show that this thing is equal to 0 times 0, as shown right here. Okay. Some people have read the book. Excellent, excellent. Slow down, slow down. All right, excellent. So since some people have read the book, all right. So nothing is less than 0. That's a theorem we had from when we started, when we were working on orders and induction, for natural numbers. So this is false. Okay. Now we're talking about loops. Are you ready? We're talking about loops now. So let's go back here. All right. So here's some observations. If the loop never runs, then T is the identity of O plus. Okay, and this observation is coded up as the fact, as this following fact. It's called empty range, right? And it is, if you have a loop and the loop never runs, you get ID O plus. All right. So if this never happens, okay. All right. So if the loop never runs, then T right here in this particular implementation, right? The loop never runs. So at the very end, T is just the identity of O plus. And that's what the rule says over here. If your loop, all right, the range is false, so we run the loop, the result is just ID of O plus. Okay, so this is called the empty range rule. So right here, we'll say empty range for sigma. That gives us 0. And what's the last step? Does anybody know? Fact 0 times 0. Yes, we could do a fact, but we could also just say definition of multiplication. Right? Yes, we could also do that. We could do a lot of. There are a lot of rules that will work. You could do a fact. You could do 0 of multiplication. You can do definition of multiplication. So a lot of sometimes. Now that we know more expressions to construct, there are a diverse number of ways to solve the same problem. All right. So before, when at the very beginning of chapter 3, there was essentially only one thing you could do. Now there's a lot you could do. All right. So, which is, I guess, more exciting. All right. So let's just copy paste this. All right. What are we proving here? How do I fix this? Does anybody want to let me know? Somebody says replace question marks with suc n. That sounds like a good idea. Let's do that. All right. Yeah. So because we're doing induction on n, right, we consider the case when n is 0, and then we consider the case when it's a successor of another number, such as n. All right. I would like to point out this cool thing right here. Notice I'm writing the whole expression, and there's no parentheses anywhere. Right. So this is, again, by precedence rules. Quantifiers don't need precedence. That means this sigma works all the way till the end of the line. So if I want something to be outside the sigma, I need to put parentheses. So if I say plus n right here, this is a part of the sigma. Okay. If I want it to be outside the sigma, I have to delimit the scope. Okay. So now the n is outside the sigma. It's not a part of the loop. Okay. If you want something to be part of the loop, you surround it by curly brackets, or you indent in some languages. In this language, you can use parentheses. So I just wanted to mention that. We'll get to it hopefully later on as well, the idea of scope. Okay. So what's the first thing to do? Does anybody know? What should we do first? So this is, people know. Excellent, excellent. So this is another loop rule, right? So the idea of these loops, right? If possible, we run the loop once, all right? We run the loop once by performing a computation, right? So this is how loops can be defined. You can say, hey, if I have O plus I with I is less than suc n spot f of I, then the way to run, the way to execute this loop, right? For instance, would be first I would do f at n, okay, and then I would do the rest of the loop, right? O plus I with I less than n spot f of I, okay. So to perform this loop, right, or a property of our loops is that when you can perform a step of the loop, you actually perform that, and then you do the rest of the loop. Okay, this is called split off term. All right, split off term. Okay, so look, it's all loops all the way down. Right. So we'll do the same thing right here. We'll say split off term at the top, right? There's other forms, right, that we have available for you. You'll see them as time comes on. So we'll just say split off term at the top. This time we're going to, so I mentioned scope a moment ago. We'll use parentheses. Okay. So now, because I want this to be outside, and I'll say suc I plus I, and I want to say I is less than, I becomes n. Okay. All right. So notice we're doing explicit substitution. So this has come up a number of times throughout this class. When you're doing replacement, you need to do explicit substitution. When you're doing contextual rules, you need to do explicit substitution. So this is something to be aware about. These slight differences that are not covered in the book because we're using a formal system. Okie dokes. Why did you use split off term at the top and not just split off term? I was just emphasizing which form. If you look, you can also split off from the bottom, right? So you can, right here, I only have top available, but later on you'll see you can split off a term anywhere, not just at the top. We're showing you that one just to get you going. If I type in split off term at just split off term, it's fine. They're just aliases. I just wanted to, but split off term, when I say it like this, refers to the more general form shown in the book, where it's for any O plus. So I just wanted to show you there are possibilities. Just as right here, I said empty range for sigma instead of just empty range. Just trying to show you the possibilities we have available for us. Yeah. Yes, so somebody asked a good question. So right here, if you remember from order theory, we say A is less than B. A is less than the successor of B. That means A is at most B. Okay. So the fact that I is less than successor of n means I is at most n. And so when I equals n, that's one of the possible cases. And so we consider that case right here, when I equals n. We take it out of the loop, we consider that case, we perform that computation, and then we add it to the result of the remainder of the computation. Okay. But wait, when you say, hey, I'm going to do this thing, and then that part, a smaller part, I recursively do it. I do it by recursion. I do that part earlier by induction, right? So these words are very related. Induction, recursion, loops, quantification, really, really related. So hopefully we'll sketch out the relationship as time goes on. But if you have a recursive definition, You can express it using a quantification, for example. If you have a quantification, you can express it as a recursive function, and hopefully we'll give you some exercises on this, and maybe in the midterm, and likewise with loops. So these things are very interrelated. Let's do the induction hypothesis, right? Since we already have that, and let's do substitution. Okay. The induction hypothesis tells us the top part is going to be n times n, and substitution tells us this is successor of n plus n. Okay, ducks. Yes, so there are notebooks available for you on Avenue to try these things, and they tell you explicitly what's available and what's not. All right. So one more step. Who knows what the final step is? Who wants to guess the final step? Does anybody want to just try a random guess? You can say I don't know. That's also a valid answer. You know, it's does anybody want to try anything?
8.6.
All right, somebody said stuff. All right, excellent. So, all right, now that people are replying, you'll see that exactly. That's a good answer. Exactly. So there are multiple ways to do it. We can also just say, for example, definition of times, and that will give us successor of n times successor of n. Right. And there's all that green. Look at that green. Ain't that lovely? Right. Everybody always wants some green. Look at that green. Great green. Right. And again, recall we're allowing you to use multiple steps. So here I used multiple steps in one hint. Okie dokes. Okay, if you want, we can do that. We can show a smaller way to write this proof. So this is sometimes called code golf. When you say, what's the smallest way I can write my program, or what's the smallest way I can write my proof? So we can do that too if you like. So here we did split off term and substitution. So we can combine these steps. I'll use a comma instead of the word and. Okay. So we can combine these steps right there, and it still checks. And we can do the same thing here. We can combine these, all right? And we can combine the last one. All right. Okay. So the proof is getting a bit smaller and smaller. This is just a single step, so we can eliminate it altogether and say by this combination of steps. All right. Here is the proof. All right. Now it will be a by. All right. Oh, I have a type error somewhere. Trying to show you things, not a good idea, maybe. So anyhow, yeah, you can do this kind of, yes, sorcery. You can fuse all these lines together if you like, and make it, the proofs get smaller and smaller. So the limit I've placed in this notebook of mine is 3. I'll change it to 4 just so you can see more of this sorcery if you like. So this last one, we can also bring it up here. All right. You will seldom do 4. The proof becomes unreadable. So it's shorter, but it's essentially unreadable now. I don't recommend you do this. You can, but you should not. And trying to do this makes it harder to understand why the proof works. So I don't recommend you do that at all. Okay? So I don't recommend you try to do this kind of nonsense. Yes, it's not beautiful. So some students will do it and be like, I hope CalcCheck figures it out. And CalcCheck might not. So I don't recommend you do this. Some students unfortunately will. I just wanted to show you that you can do it. Yeah, it isn't satisfying. Good, excellent observation. It's not beautiful. It's hard to read. It's going to have mistakes. So I recommend just write it out. Take the extra second to do so. It's not a big deal. Alrighty. But I hope you enjoyed that interactive theorem proving, which is a real thing, interactive theorem proving. So we'll get to that another time. So we talked about these. I'll just go over them quickly now, just to remind you. Right. When you never execute it, it's the identity of the operation. The identity of plus is 0. The identity of times is 1. So need to remember what the word identity means. Okay. So this is back here. All right. If it never runs, it's just the identity. All right. And then we talked about splitting from a split off term. You can split off from the top, all right, and you can split off from the bottom. All right. I didn't have better names for them. Just I thought it would be helpful to refer to one side as the bottom and the other side as the top, because you're working with a range. I guess could have called them split off to the right and split off to the left, but I think they're okay names. And that's just about if you can run it, at least do it once. Right? So in our proof below, we didn't have to split off. We split off from the top, but we could consider alternate ways to split off. So I just want to let you know there are other ways to do these proofs. This looks very similar to our proof, so I won't walk over it. Later we'll get, so right now we're working over the natural numbers, but later we'll get to the integers. And now there's a proviso, right? Instead of being 0, we consider an arbitrary integer m. And of course, for this to be not empty, right? Remember right here, it says if possible, right? If it's possible, right? So if this range is not going to be empty when m is actually less than n. If you take m to be 100 and n to be 0, this is going to be false. There's nothing that's at least 100 and less than 0 plus 1. So that's what the proviso ensures. It ensures that this is actually non-empty, and so you can split out a term. Okay. That is not a cat. My baby was crying. He is not crying anymore. He was napping. But I'm glad somebody's listening. So here's a cool rule we didn't talk about. This one is great. So let's talk about this rule. This is a nifty rule. This is a you can think of this as an optimization law, right? Looping over a large input can be made, quote unquote, faster by splitting the input data, right? So whenever you have a list, you're getting a bunch of information, you can consider, all right, let me do the first part and then the second part, right? Because they're disjoint, right? There's no overlapping between the two parts, right? So for example, I have two people working on organizing some books, for example. I give someone half the books and the other person half the books, and then they can organize them independently. That's much faster, right? So this is the idea of divide and conquer that you see repeatedly in programming, and it shows its face as a range split rule, right? Recall we called this part the range, the part in the middle, and here we split it, right? And that's okay because they have no overlapping parts to them, okay? You might remember this if you took grade 11 data management. This is also sometimes called the principle of inclusion and exclusion, where there's no commonality, and so we don't subtract any other part. Okay. All right. So I'll just write that down as well. O plus I such that with Qi or R Ri spot Fi. This is equal to slash O plus I with Qi spot Fi slash O plus I. Just a question. Would you prefer that I keep showing you these O plus variants or not? If the majority vote is no, then I will stop doing that. Provided Qi. Okay. So I don't know what the word no means. No, you want me to stop, or no, I should not stop. So O plus just means any operation, like plus or times or where O plus is plus times and or max min GCD LCM. What else have we covered? I don't know. Meet, join, equivales. So it can be any of these. Any commutative monoid operation. All right. Okay. So recall we talked about commutative monoid operations, but the idea is I'm using O plus because the rules will work for all of these operations you've already seen or will see. All right. Okay. I'm seeing a lot of likes for a lot of different comments. Okay. All right. So, all right. Iman, I'll get to your answer in a minute. Okay. So it seems like you like that I show you this uniform form. So I'll continue showing the O plus versions. I don't want to waste your time on stuff that's not that interesting. So I'll continue doing that since I think it's useful and you think it's interesting to have. Someone was asking about this rule. If Q and I were not overlapping, right? So let's so if Q and R were not they were overlapping. If they were overlapping, i.e. had a solution I in common, then the left side, then the right hand side would have Fi repeated twice. Had a solution I0, then the right hand side would have I twice, right? More than the left hand side. Okay, so here's a simple justification of why this would be the case. On this side, if I ever have an I0 that makes both of these true, then true or true is just true. So that's fine, and I do f of I0. But here I get f of I0 and f of I0. So I have f of I0 repeated twice, which is more than the other side. That's why you need this. Okay. All right. Were there more questions? Yeah. So that's exactly what this says. They have to be exclusive. That's provided Qi are So that's exactly it. I.e., they are disjoint, right? Exclusive, complementary, right? Okay. So that's what that part says over there. Okay, next. And of course, it works for other operations, not just plus. It also works for multiplication, and as I mentioned over here, it works for and, it works for or, it works for these kind of things. So just as a reminder, sometimes plus is written as sum, when you write it as a quantification. Times is written as this big pi symbol, and is written as this upside down A for all, or is written down as this backwards E. So sometimes you'll see these a big form or big operators, and that's what we'll use for calc check. So for parsing. Okay. All right. You're welcome. Good. Alrighty. So here's a really cool one. And again, this is another form of the loops, right? If the loop never runs, this is what it is. But if the loop runs only once, then the only possible term is the result. Okay, so this is called the 1 point rule. Okay, and it says if you have an O plus I, with I is equal to some expression E, then, and you have here f of I, for example, the result is going to be f of E. Okay, where I cannot occur in E. Okay, all right. So this idea is, for example, I think it's Henry Ford who said, you can have any car color you want as long as it's black. Okay, you can have any color as long as it's black. That means you only have a black colored car, right? So there's the idea of free choice, but really there's only one choice, right? So here we're looping over all the I that are equal to E. Oh, okay, then that's just one possibility. There's only one point, right? So the left side says, consider all possible I's that are equal to E. Okay, and there's just one, okay? And the proviso is I cannot occur in E because what if I said I equals I? Now I'm saying you can consider all I that are equal to themselves. Oh, okay, that's still all I, right? So I haven't, that's very special case. Okay, next. Does Isra, are you guys still there?
Yeah, we're here.
All right. Okay. So here is a simple example right here. 5 plus 2 times I is less than 7. By some arithmetic, right, you can show, remove the 5 to the other side, right? 7 minus 5 is just 2. And then 2 times I is less than 2. Divide by 2 on both sides, and you get I is less than 1. But I is a natural number. The only natural number less than 1 is 0, right? So I equals 0. And then we can apply the 1 point rule to simplify this. And again, you have to use a, you have to use substitution. So let me show you this. Calculation. I have the sum over all I natural numbers with I equals 0. Spot 5 plus 7 times I equals, and right here we say 1 point rule for sigma, and that's just 5 plus 7 times I with I becomes 0. So as always, there is going to be a substitution step. Okay, so that's 5 plus 7 times 0. Okay, so whereas the book will jump over the substitution step, we always have to do it. Okay, and then you can just evaluate. Alrighty. Okay. So we are going a bit slower than usual, but I think we're learning more, and I'm glad we are. So I want to show you all these slides at once, but unfortunately my screen is just a bit tiny. All right, so let's focus on these top two. I talked about a scope a moment ago. So let's do the same calculation again, but this time let's add some extra variables. Let me say plus I right here. Okay, does everyone? This is very, very subtle. This is very subtle. Here's a plus I. Okay, now I'm going to put some parentheses. Okay, plus I, plus I. Okay, so notice this I, this plus I, is not under the sigma. It's not, the parentheses of the sigma closed. They're in this purple box. And so when I do the 1 point rule, only the stuff, only the body part of the sigma is affected by the 1 point rule. Right? And then when I do substitution, only that one. This extra I is just a variable that's sitting there. Right? It happens to have the same name as the variable of the sigma. Okay? So this is the idea of scope. This I is not in scope of this sigma. It's like having a for loop. I have a for loop, all integers I, and then I also have a global name I. Okay. You and your friends are chatting, and your friends are talking about Jasim and Jason, and you know who they are from your friends group. There's a Jasim and a Jason. But you go to another friend group, and they have a different Jasim and a different Jason, right? So the names Jasim and Jason refer to people that you know in your friend group, in that scope of relationships, right? In different scopes of relationships, the names Jasim and Jason refer to other people. Okay, so that's the same thing. When you think of a lecturer, right now you think of me. I'm your lecturer in this time frame. But later in the day, you'll have different classes, and the word lecturer will refer to someone else. Okay, so this is the idea of scope, right? Things refer to different things depending on the context you're in or the scope you're in. Okay, does that good? All good? All right. And the idea is that this I right here, this I in the parentheses, belongs or is bound to the sigma. The sigma tells us how, the lifetime or where you can refer to this I, right? So this I can only be referred to in the parentheses. So if you want to refer to this particular I, you have to do it in the parentheses. Any other reference will not be to this I, okay? When we're talking about my friend Justin, and I'm like, oh, Justin did this, Justin did that. If I'm talking to my friend group about politics, maybe Justin refers to Justin Trudeau. If I'm talking to my kid cousins, maybe they think Justin refers to Justin Bieber. Okay, so and some of us like one Justin more than the other. So depend if I'm driving my kid cousins in the car and I talk about a Justin, that Justin refers to the one they're interested in. Then when I get out of the car and I see the word Justin, it refers to someone else. Okay, so the scope is delimited by these parentheses. Okay, I'm looking here. I just want to make sure if people are mentioning. I am just trying to see if anyone's. No, okay.
Yeah, I think we're good.
You're good? Okay. I just thought maybe the screen froze, and I'm like, oh no, maybe my internet connection is bad, which has happened before. Thank you, Isra.
You're welcome.
So this idea of being bound or being scoped by a quantifier is something you've already seen. For example, in calculus, the purpose of this little d, right, in calculus, for example, is to tell you, hey, the thing after the d is the variable that we're using, right? So this x is part of the quantification. And when you write functions this way, the point of writing f of y equals something is to say y is the variable. Okay. Do you guys see the star action I'm doing right now or not? This fireworks?
Yeah, we can see it.
All right, so I make sure that you can see it too. And likewise in programming, the idea is you declare the variable to say, hey, this is the input to the function f, it's x. Okay. Here, q, notice q is local. It's between these two parentheses. Q is local. It lives inside this scope. Outside of this box, when you say q, you refer to a global name q. Okay. When I say the word Obama, almost everyone unanimously thinks of the previous president of the United States, Barack Obama. All right, most people think Obama and they think him, but so that's a global name, Obama. If I tell you, hey, I have a duck and my duck's name is Obama, right? Then I've introduced a new context where the name Obama refers to my duck, right? But outside of this duck setting, Obama refers to the president. Okay, so this is the idea of scope, right? Depending on the scope, refers to a duck. Outside of it, refers to someone else. Okay, ducks. Yes, it's for carrying the whole glass. Yes, and ducks all the way. Or when you say let clauses, temporarily let Q refer to this thing. All right, well, outside of this let clause, Q refers to a global name. Okay, ducks. We're out of time, so that's unfortunate. But I just want to talk about this occurs meta predicate, which why I secretly mentioned down here. I silently mentioned it. So we'll get to it next time. And I hope everyone had a wonderful reading week, and thank you for coming to lecture. I will still be here, but I'll stop this recording for now. The people who have to leave,